that density where a visible shrinkage cavity will occur. We've been running with the fast and loose kind of anywhere from 50% to 70%. There's probably going to be a hole, but we want to nail that down probably to within a 5% window instead of a 30% window. And then following that, we're gonna prepare for the casting of our first parts. We're gonna make our patterns, like get ready to make our molds, and then we're gonna cast everything. And then following that first casting day, we're gonna analyze our parts. Cross section them, see if what we predicted to happen in solid cast and with our preliminary casting experiments was true. See and just kind of verify our results based on our simulations and all that. And then afterwards, we're going to revise kind of everything, revise the pattern, revise the gating system as needed, and then cast again. And then, hopefully that'll be much better, if not exactly what we need. So then following that, we can do some more minor revisions, maybe bring in the towel hook, see if we can play with that a little bit, and then cast one final day to, get everything that we want. Following that, we're gonna butter them up, get them nice and ready to be used for the materials manufacturing course. And then we're going to begin our final report construction. And then finals week will be finished and present again.
Alrighty, so for our budget, so we're casting with a 356 alloy of aluminum. So we are going to need a lot of aluminum bricks. So we have about 40 pounds that we're hoping to be able to get. And then we are also going to be making match plates, which are kind of a cookie cutter that you put in when you're packing your sand to cut your pouring cups, sprue, all that good stuff. So we're going to get a sheet of plywood for that, a closet rod to cut up and make little risers for inside our molds also, and then a roll of filament to 3D print our patterns so we don't use all Dr. Patterson's filament from downstairs. So that totals about $500, and then we filled out the grant request and turned it into Dr. Hart, and then we were awarded $750 so far.
And that will conclude our presentation. Thank you all again for your time and attention. And we wanted to give one special thank you to Dr. Barnicky. I think I can speak on behalf of the team when I say we've appreciated getting to work with you and learn with you, learn from you over the past couple months, and we're looking forward to continuing that in the spring semester. So thank you.
Thanks.
Any questions at all?
Yes.
Yeah, I got one. You talk about the sensitivity of solid cast. What is the smallest size defect that you can see? That you could model
For a particular part.
Yeah, for any part or the part that you have, whether it be the shift fork or the tunnel forecasting.
So do you mean like smallest detail in terms of like your element size, or smallest detail in terms of?
You kind of mentioned in one of the criteria that it had to be sensitive enough for SolidWorks to see it.
Yes. So the primary motivation behind that is, as you can see in our pictures from our solid cast simulations, right? You would have that little yellow iso surface of that density. We want to nail down exactly what percentage density will cause a visible hole, and then make sure that like you can see that in solid cast and it matches what the actual part does.
That's part of the first thing we do when we come back is narrowing down what that number is. Sure. So what percentage is going to be the threshold between when we cut it open and we cross section it, we can.
But we're hoping for about a void of a few millimeters, just something we can see without any microscope usage.
Okay, so you do have a number in mind for doing a macro analysis of the size of a defect that you can see.
Yeah.
And I got a follow-up question to that. So you got a slide there about radiography. Do you know what the sensitivity of radiography is in terms of?
For flaw detection?
Yeah, for.
Ooh, I don't, I'm sorry.
Not sure.
Yeah, I don't know what an X-ray can get for flaws.
Okay.
I think the crux of the project was to have a flaw that's big enough to see with the naked eye.
When it gets passed around class. So I don't know if we would be using.
I'll be real interested to see what correlation you get between a SolidWorks model and a real part, because like you might have a 10 millimeter sphere that shows as a flaw at like 90% density, okay? But that doesn't mean you're gonna get a void that big. You're gonna get like a 1 or 2 millimeter void from that 10 millimeter area, or whatever that correlation is. That'll be real interesting.
Yeah, I'm actually think it'd be interesting if to actually send those parts out for radiography.
Yeah.
I mean, just in real life,
Yeah.
you don't
Right.
really get a chance to do destructive. Everything can't be a destructive test for you slice, right? Most of the time you have something that's either UT radiography or CAT scan, you actually send through a CAT scan and do.
You could do that before you slice it up, then you know where it comes.
That's true. That's true.
Aim for, I saw this on an X-ray and I want to slice right through it. Here are those pieces.
Yeah, I got two more questions. How are you gonna differentiate between shrinkage and, for example, oxide and dross? In terms of like defect, like how
Are
you
you
gonna be
talking
sure?
like microporosity,
Well, how you gonna be sure it's microporosity versus perhaps something from the melting process that you've done?
Ooh.
Some junk.
I'm not totally sure. I think microporosity, I don't know if I don't want to say we don't, we're looking for something bigger, so I don't know how we would be able to differentiate between that and more of a solidification problem in solid cast. I think we'd be able to see it, right? I don't know if solid cast catches microporosity.
Oh, other way around, you should find,
We
you should be able to model the microporosity
easier.
in solid cast. It's the other stuff that's actually really difficult to find. All the oxides, all the dross, and partly depending on how you orient your part, it's gonna make it a real big problem.
I think that's
Because
the
all your,
purpose. Oh, sorry.
no, go ahead.
I think that's the purpose of having so many test castings is to not only because we're controlling for the material quality by hopefully using the same manufacturer for the aluminum, but then also doing a lot of different test casts and making a lot of revisions just to see how those things correlate. And then when we do destructive testing, we can, kind of fine tune it so that when we do see flaws, that they are definitely shrinkage.
Okay. And this is the last one. That's actually related, but do you have some research about the parameters that you're gonna cast this at? Like,
Parameters meaning,
specifically, superheat, how much, where are you gonna take this when you melt your aluminum? How hot you gonna keep it?
so we're planning to use generally the same kind of standard that is used in the class. So whatever the
I
melt
think it's
temperature.
like 1350.
Yeah,
Is it
so
1350?
whatever the temperature is in the actual class, we're planning on using that basically.
Okay,
Because like this kind of goes hand in hand with the casting project that they do in that class. So it would be nice if we could kind of mimic the same type of situation that they're gonna experience.
okay. Perfect.
I guess. Just generally, how big is this thing?
Like that. We had dimensions. I
So
have
about
drawings.
as large as you could fit inside the plastic
Yeah, there,
that we have here.
You can probably, let's see, it's
you can see.
4.5, say 6.5 inches
Okay,
square.
yeah, it'd be good to know that, because I'm sure can't read it off of here.
Yeah.
Sure, I'm just saying, as a presentation, if you're gonna have a picture with dimensions on it, that would be helpful, and this doesn't work, so just make that real big, or let's just say it's about so far. Yeah, good. Are you considering variations? Like good and bad practice, you could do a lot of things to make this same part, so if I saw you're moving the dating system around, are you considering different orientations up and down, or parting line in the middle versus
Well,
different things you're gonna consider?
because of how the shift fork is, there's a lip. Let me see. Yeah,
I'll go back to the there.
so there's a lip here.
Yeah.
And unless we take that lip out before casting, it can only be cast bottom way. Well, because when you,
If it was, you could have it sitting above the party, you could
Right.
have it sitting in this orientation and completely above
On
the
the
party
top.
line. Or flipped over and completely below the party line,
Or in the middle, right?
or half and half.
I think to that point, because the our solid gas simulation showed that like the major area where we are likely to have a shrinkage cavity isn't related to like this area, like that orientation. We certainly could and probably should, like play around with that orientation. But at least right now, I don't think that it would cause a difference between.
It
where our
would change
hole would be.
the height difference between your riser and the part, and so the tendency to flow from the riser into the part would different depending on where the part is.
I think right now we're looking more at the effects of changing the actual part geometry, and then looking at the gating orientation is more like a secondary effect.
Yeah, I kind of agree with that. Our main focus is per design, then second is.
Okay, so
Yeah.
primarily part design.
Right, this,
Gated
this,
system design.
the idea came from that CV
Okay.
joint. Yeah, so a
makes
part,
sense.
yeah, so they're tasked, they were tasked to have a part that gating system could not make better.
Okay.
Yeah.
That makes more sense. How are you planning to cut these apart?
So the shift fork, you stand it up on end and cut right down the middle.
Right.
With- Cut with what?
Probably the best stuff.
Yeah.
Might, if you can find somebody to water jet cut it for you,
Ooh, that
that
would
would
be
be a
nice.
lot
You don't have to
better
work.
way to look for. I've cut up a lot of, like, in the past, cut up a lot of parts to look for porosity, and bandsaw tends to like
Yeah, it's,
smear over and obliterate what you're trying to look for.
Figure out when you get to
Very much.
Yeah,
What about you?
If you know a guy, we're open.
I wish somebody on Baja or Longmont. No, that's it.
That's it? Anyone?
Very nice.
Anyone else? Okay, very good. We are 2:13, so awesome on time. So you guys have the next group. Thank you.
Thank you.
Good job. People are like popping in and out.
Yeah, well, you can hear it like.
I know, and I'm like, and then somebody had their mic on.
Yeah, I heard that too.
And then I turned it off, and then I got a chat saying I muted everything. I'm like, I should not quit my day job.
IT is not your strong suit. Right.
You want us to wait like the
Till
full minute,
2:15.
or do you just want us to like rock and roll?
I mean, we got 50 seconds.
They never responded to my email, so I'm gonna go with no.
There is
Is it a John Williams?
there's a John Williams.
Hi, John.
I was-
Okay. Is that who you were
That
expecting?
is-
It is John, and then I
Yeah,
think Patrick.
And as long as they're online too,
Patrick
then we're good.
counted it.
Yeah.
We could also just talk another, we could probably extend this another 30 seconds.
Yeah, it's online, then-
Yeah,
Yeah.
I think we should be good because they said that Patrick would be out of the office.
Sure,
For the baby.
for the-
let's go. Maybe the baby's on, watching online. Whenever you're ready, you take it away.
Hello, everyone. Thank you for taking the time out of your day to join our presentation discussing our senior design progress. My name is Anthony,
I am Jimmy Webster.
I'm Caitlin.
I mean, it's
and our senior design advisor was Dr. Schaefer. So for our senior design project, we chose a softball corrosion chamber, which is sponsored by Mizumi. And although they're not here, you heard before, John Williams is virtually with us. So the goal of this project was to create, design and construct a tabletop salt spray chamber for corrosion testing to be done at Mizumi. And the system will be able to complete a 7-day corrosion test without service, adhering to the JIS standards. And to get a part like reference size, Caitlin will hand out some parts that we got from Mizumi when we visited them back in October. So a brief overview of what we'll be discussing today is the final design, constraints, design concepts, assessments, preliminary budget, future plans. Now hand it over to Jimmy to speak about that for this one.
So the short video is an explosion created in SolidWorks, and its main purpose is to highlight some of our key components of our final design. So we chose to go with 4 fine meshes as our means of producing a salt fog within our chamber. And then, as you can see, the small rectangle coming out is the part rack. It'll be fully removable, and then we'll be able to put the parts onto the part rack and then load it back into the chamber. And then next to the chamber, you can see the small cylinder is one of our storage tanks. We'll have 3 in total. One is for the storage of the clean solution, which will be pumped into an internal tank. And then all of the waste will be collected in a 3rd external tank.
Okay, so for constraints, we use our constraints kind of like guidelines to build our initial designs. One of the main constraints that we got numerical maximums and minimums from was the JIS H8502 standard, which is all about corrosive testing as well as the duration of those tests. The JIS standard gave us some feedback as far as like the size of the chamber, which needs to be 0.2 meters cubed as far as the chamber of testing goes. So that only accounts for the internal chambers. It gave us flow rate for both water and air. The flow rate of the water needs to be 1 to 2 milliliters per 80 centimeters squared per hour. And the flow rate of the air needs to be 1 meter per second for 1 second per hour. The solution itself needs to be 35 degrees Celsius, which with a range of 1 degree Celsius of that. It needs to be 5% salt water, exactly 5% salt water. The last thing that the standard gave us was that the orientation of the part needs to be held 20 degrees from the horizontal plane. Secondly, the environment that our chamber is going to be put in is not like a lab space, which would be really helpful, but it's an office space. So with the office space, we have like a tabletop that it's sitting on. This tabletop is 600 millimeters by 900 millimeters with like storage underneath to put external chambers like Jimmy was talking about with either waste or clean solution. With the environment of an office, obviously noise is a bit of a big hitter. We have a maximum decibel rating of 75 decibels. At no point can we cross that line during a cycle. And then finally, the test length. The JS standard says that test runs for 7 days. Mizumi added an extra constraint to that, saying like they'd like it to be able to run without having to service, so you don't have to add water or anything like that to it during that time frame, so they can go home on the weekends.
So I'm going to start by talking to you guys about our first design concept. The first one is a dual fluid valve nozzle. So as you can see from this outside, this external image, is we have an external tank being fed into an internal tank. And then from the internal tank, there's a heated feed line of solution. This line will lead to each of the 4 corners where our nozzles will be located. And to talk about the nozzles a little bit, we would have to have an air compressor located on each side of the internal chamber, and those would be compressor packs. And the compressor pack would add in compressed air to the nozzle as well as fluid at the same time. So we would have solution going in, air going in, and then they would be combined inside of the nozzle and then released into the chamber itself. So to look at it again, we would have 4 nozzles, and they would be released in staggered motion. So we'd have 2 at once and then 2 releasing in the next few minutes, just to allow for our compressors to reach their full potential, because we have a limited lifespan with the amount of time that we would need it to run in the 7 days. And in addition to this, we would have 2 fans located at the bottom, and this would allow for air circulation to be happening, which is really vital to our JIS standard.
So our second design concept was the fine mesh screen, which we did end up adapting to our final design. And so the means of creating the fog, as I mentioned before, would be 2 fine meshes located on top of the chamber. So the water would be stored in an external water tank and pumped into an internal water tank that we would have a submergible water heater in. And then upon reaching the 35 degrees Celsius temperature, it would then be pumped to the 2 meshes. Inside the chamber, we would also have a vacuum, which would serve to vacuum out any of the fog if the trial were to be paused or upon completion of the trial. And this is, the main purpose of this is to help minimize the salt that leaks into the office, because like we said, it is in an office, so our goal is to not coat the desk in salt. The part rack will be removable, but it will be fixed at a 20-degree, there will be pegs fixed at a 20-degree angle in each of the corners. And at the bottom of the chamber will be a drain to collect the runoff. And also there will be a single fan inside to get the forced air movement as per the standards.
So the third design concept was mine. It was a rotating fan concept. The entire system kind of works like a sprinkler system would in a building. Look more closely at the nozzle. It's two parts. Both parts would be machined here and not bought, which was kind of one of the bigger issues with this design. The first part would be a spirally grooved cone. The cone's angle would be able to change to modify the spread of the fog. And then the second part, the first part would be attached to the gating system, and the gating system would break water particles into smaller particles, so that would help kind of like make different size fogs, so it would hang longer or not longer by changing the gate size. So the overall structure here, we have a box over cozy to kind of like a restaurant plate thing to kind of contain the corrosive air, and then it would all sit on a 3D printed tray to kind of keep it self-contained and collect any runoff. And then I was going to heat it with inductive lines instead of a space heater like Jimmy's.
Okay. With the last design concept, the way the fog is produced is using an ultrasonic diffuser. An ultrasonic diffuser creates fog by controlling an electronic frequency, and this generates the vibration of a ceramic disc, all while submerged inside water or like the solution of use. A fog is created because the vibration converts the converts the solution into microscopic droplets that can be propelled into air. And then the image here you can see is just like a side profile of how the fog will travel from the solution reservoir to the mist outlets. So there are two fans in this design. First fan, you see this image here. It pushes the fog produced the reservoir into the test area. And then the second one is the mist out or flush to the mist outlet here, which will allow circulation of the fog. Another way the fog will be distributed is through or by the use of electrostatic plates against the back wall. This is done by charging the solution inside the reservoir, and then the plate will be turned on once the door is open to keep the fog kind of contained. And to ensure the solution is kept at 35 degrees Celsius, a water heater will be placed inside the solution reservoir, and another heater will be utilized inside the chamber as a space heater to keep the air at 35 degrees. A part rack will also be used in this design. It will be held with pegs placed at the four corners, and since the rack needs to be held at 20 degrees per the JS standards, a 3D printed parts holder will be attached to the rack to keep them in place. And then for the drainage system, the flow will be slow to allow the wastewater to be collected at the center. And then this would be manually kind of disposed of by the user.
So in order to decide which chamber we were actually going to select, we decided to make a decision matrix. And we ended up having 5 different criteria that we wanted the chambers to be based off of. The first one is Mizumi components. We wanted to have at least 90% Mizumi in our design. This is mainly because Mizumi really wants to use this as a trade show piece, and they're going to be able to use it to show the variety of different components they have for customers. So it was a really important criteria for us and Mizumi. Next, we have usability. So we want this chamber to be easy to use. This means an easy to open door, close, and in addition, we want it to be able to be paused. So for the entire 7 day span, there's a chance that Mizumi will want to pause it to take pictures of the parts, look at the parts, or if you're at a trade show, you don't want to run it for 7 days. It really won't work very well at a trade show for 7 days. So we want it to be able to be paused for easy use. So basically, easy to use, easy to fix, and easy to pause. Next, we have noise. As was previously mentioned, this is going to be an open plan office space. So an open plan office space has usual decibels from 50 to 65. We know that our actual chamber won't be able to run for the entire time for 50 to 65, but we want to make sure that we're around that area for most of it. But as you guys heard from our previous, all of our designs that we have components like air compressors, vacuums, ultrasonic diffusers. The likelihood of us being able to stay at 65 decibels is just not very likely for the entire time, which is why we wanted to build in 70 to 75 decibel spike allowance for around 2 to 3 minutes every hour. Next, we have cost. So currently we have $2,200 for a budget. We have $1,200 granted to us by MSOE and $1,000 pledged to us from Mizumi. As you're going to see later on, our budget is getting relatively close to that already. But luckily, we have had conversations with Mizumi if we need to go over budget. Next, we have saturation. Now you might be thinking, saturation is a pretty important part of salt fog corrosion chamber. And yes, you would be right. But the thing about it is, without building each of our chambers individually and testing the saturation rate, we wouldn't be able to really know what it would be like. So we wanted to make sure that it was a criteria, but we would have to take an estimated guess at what it would be like. So the 3 highlighted up here are what we decided were the most important for our chambers itself. The way that we ranked them was scoring all of our chamber designs for each of our criteria, 1 through 10, and then multiplying it by our weight. And Anthony is going to talk you through how we did that.
Yeah, so after defining our criteria, we assigned the values for each of the design that you may see on the screen here. When summing up the scores with the weights applied, the mesh and the fan came out on top. And as you can see, like the mesh and fan were very similar, or had very similar scores. But the only difference is the fan had a score, or the noise for the fan came out to a score of 9.5, and the mesh came out to 8.5. And that was determined by because there's no vacuum inside the fan did not use a vacuum for its design, and also for the fact that the air compressor used will be enclosed. So our team chose between these 2 designs due to the fact that the scores were very closely, or were close enough due to the uncertainty in our assigned values. But to decide how to move forward, it was predicted that with the fan, it would take longer than the mesh design to produce. This was mainly because developing the moves of the spiral, the case, and the nozzles, it would take much longer than fine tuning the mesh design. And then, so with that said, the main reason why we didn't go with the highest score was because the amount of machine parts that would be used is would hinder our ability to complete the project full time. And also, if the fan were to break, it'd be a little harder for Mizumi to kind of recreate the parts. So that's why we decided to go forward with the mesh design.
So as Anthony mentioned, we decided to go with the fine mesh design concept. However, we made a few adjustments to it. The first of which is we decided instead to use 4 fine meshes instead of 2 previously, because the cost to go from 2 to 4 was negligible, and we thought we would get a better saturation within the next is we stayed with 3 tanks. However, instead of heating the internal tank, we decided that we would heat the lines moving from the internal tank to the meshes, because this would significantly reduce the cost between the 2 of them. And then we also decided to add a second fan into the chamber, to increase the air circulation, again, hoping that it would provide a better saturation. And the cost for an extra fan was equivalent to a submergible water heater, so our overall budget was not affected by this decision. And then everything else from the mesh design was kept the same in our final design.
So here we have a preliminary budget of our final design. This is pretty much everything that we could think of that would be like large chunks. Now, this doesn't up the budget. This does not include like every bolt and nut, but it's pretty comprehensive. Everything here was sourced directly from the Mizumi website or their catalog and priced by Mizumi's website and catalog. That the one exception to that is those internal pumps on the top there. The submersible internal pumps from Mizumi are like really, really big, and they move way more water than what would be necessary for our project. So we source them from a different place just for cost, as well as not having to move gallons per hour when we need milliliters per hour. And then the total of this was just over $2,000. Again, that's kind of getting close to the upper limit of our budget, and Caitlin will kind of explain why.
So the 4 highlighted components on this screen are the big hitters that we have at cost right now. So as you can see, the polycarbonate is taking up a very large component of our budget that we have. And this really comes down to the fact that Mizumi has the ability to cut our polycarbonate to size. And we do need polycarbonate like to a very specific length and height. So we would otherwise need to either do it ourselves or send it to a machine shop to have it done for us anyway. And if we were to do it ourselves, the likelihood of us messing up and having to buy another sheet of polycarbonate would set us back in budget and time. So we decided to just eat that cost and just go with what Mizumi is able to do for us anyway. And then as you can see, our extrusion connectors is very high in budget as well. This includes gaskets, screws, nuts, bolts, everything we need to keep our entire chamber together. But you might notice that we don't have control systems, piping, or tanks on our actual budget right now. So our budget is going to increase in the next couple of months once we start adding those in. But luckily, we have had a conversation with Mizumi about this, and they're willing to work with us to make sure that we're getting high quality but low cost parts off of their website. And they're willing to work with us to make sure that this prototype gets built.
So finally, for next semester, we got 2 main things that we're going to do. First of all, we got to build it. And second of all, we'd like to test it to make sure it actually works. So in this build phase, we're planning on submitting a more accurate bill of materials over Christmas break, so we can start receiving parts throughout the first few weeks of next semester. During this build process, we are expecting like 2 major challenges. That would be both of them meeting the JS standards, A, of the flow rate. So we don't really know exactly how it's going to, like how much water we're actually going to get out of these nozzles per hour. So we'll have to play with things like the pressure in the internal tank and things like that to make sure we meet that standard. And secondly, the temperature of the solution as it reaches the nozzle needs to be 35 degrees Celsius. So either lengthening or shortening the inductive line heaters would be the way to do that. And we don't really know exactly how hot or how cold they will make it at the moment. And then secondly, once we have a chamber that fully conforms to the JS standard and our other constraints, we would like to test it. We have 2 main tests that we're thinking about as of right now. The first one would be the testing of evenness of saturation. This would be done by taking 4 exact same sponges, putting it inside the corrosive chamber, and then running it for a full cycle. At the end of that, we'd like to weigh them and ensure that they're in the same weight area so that they collected the same amount of water. The second one would be a noise test, and the noise test would be performed by putting a microphone 1 meter in front of the chamber and running it for a full cycle and making sure that A, it's mostly in that acceptable range that we've previously defined, and B, making sure that it definitely doesn't go over 75 during any portion of the cycle. My team and I would like to thank you guys for your attention and time today. Do you guys have any questions?
How did you guys determine the noise level of your system during the ranking?
Yeah, so for the noise level, we did some research about what the average noise level in an office space is. And we went off of like an open floor plan of an office space. There is a potential that the chamber will be in an enclosed office, but we wanted to go off of the idea that it would be out in the open.
And then to rate each individual one, we took like the average vacuum. I know Jimmy had the vacuum in his, and he has like an actual part from Mizumi that is rated at a certain decibel rating. Same as the compressors and the pumps, they all have certain decibel ratings, which was a nice part about getting them all from Mizumi, is they kind of came with those. So we basically were guesstimating based off of like, hey, it's rated for this and it's inside 3 chambers, or it's on the very outside, you know, so that's exactly what you're getting. So that's kind of how we rank those as far as noise goes.
So how did you choose your materials?
Yes.
And
A lot of it came from what Mizumi has, and the aluminum extrusion is just the very common. It's also known as 80-20, but Mizumi calls it extrusion, so we call it extrusion. And the thinking is that there is a potential that we might need to coat the inside of the aluminum extrusion with some kind of rubber or silicone to prevent any kind of corrosion.
actually, my question was more on how did you account that you're intentionally corroding things? Like, so the materials that you're.
Right, so there is a potential that like the aluminum could need an extra coating on it to prevent the corrosion. And then the polycarbonate itself is relatively corrosion resistant, but there's also other kinds of plastics that we're looking into to potentially substitute in.
Yes.
Okay, so I'm wondering where the air is coming from that you used to spray the thing on it.
The air?
The air.
Oh, yes. So in the actual design, a lot of the power so like the actual power that's going through the water, it's going to be coming from a pump inside of our internal tank, and it's just going to be pumping the actual fluid into the meshes, so there won't be any kind of compressed air.
It's very part specific, right? Like, these are the parts that you handed out, that were the actual ones that
Yeah,
are being tested.
so these are a kind of part that will be tested. These are the ones that they provided to us. They said that this is the general shape and size. There could be other ones that are used. These are just staking pins that they use for engine blocks.
Okay.
Yeah.
Are there specific number that you need to fit into
12 to 20.
They said, yeah.
one lot?
Yeah.
But they also said that there is a potential that they might want to do like a one-off. So they might just want to throw one in and
Sure.
not have the entirety of like 12.
I have one other question, kind of with regards to this, the evenness of saturation. So it's specifically you want uniformity, right, in your chamber?
Mhm.
Is that test with the sponges? Is that the JIS test, or is that one you?
No, that's one that we came up
That's
with.
one we kind of just,
brainstorming.
yeah.
Dr. Schaefer helped us come up with that, actually.
The JS standard calls for like a humidity spread as well, which Mizumi was nice enough to tell us that we didn't have to do, because the sensors are pretty expensive and we don't have access to like that kind of resource, I guess. So that's why we're not doing like the JS standard testing as far as like, you know, humidity levels in the 8 corners of your boxes. So
Just a follow-up. So if you were to find some variability within that bond, what would you change?
So the main thing that we're looking at right now is we're currently using the smallest grain of mesh they have available to us at Mizumi. So we're considering either creating different shapes with the mesh, potentially like a hemisphere or something to help with the spray and the spread at which it is going, or adding in a nozzle to where the fluid is entering towards the mesh to help with that.
So strictly just the location and the.
Yes, like the location and the angle at which it's gonna go in and hit the platform itself.
So it seems like it's a big fluid dynamics problem.
Yeah.
Is there anything like secondary fans that you have to send through there, so you have a flow pattern?
We have secondary fans on the bottom helping circulate the air. I'm not entirely sure if we're gonna add any kinds of fans to the top of it, because currently we do have the top opening. And so if we have the top opening and there's fans located on it, the potential of air escaping through the top and then coating the office in salt would be pretty high. And that's not really something we wanna do. But adding them to the sides or entries of where the actual solution comes in could be something that we add.
Thanks.
So did you, in your research, look at, what's involved in existing salt chambers?
Yes.
She actually went and saw some for us. Go ahead.
So we had the ability to see a salt fog chamber and what they look like. And the one that we were able to see is much larger
Yeah.
than the one that we have. So has access to shop air, the ducting system of the shop. So some of the challenges that we're running into are not ones that are typically seen in a salt fog production, but it's very similar concept with a enclosed polycarbonate box with fluid going into it. They typically only have one nozzle at the entry, and then it just fills the box because they're able to use high pressurized air from their shop and have a pressurized tank of fluid. Since we're not able to do that, it's a little bit more of a MacGyvering, I guess, to the problem. But I think we're working through this.
Now, is this gonna be powered, is your power source
It's a 12-volt outlet.
wall outlet?
Yes.
Is there anything special you need to consider in the fact that you've got salt water and electrical?
I mean,
Are there like,
Yes.
are there certain standards or codes that,
not that we have looked into, but definitely something that we will. I think the main thing that we are worried about is coating the entire office in salt currently. But it's something that we're actively trying to prevent by sealing everything in. And we're hoping that the wall outlet will be far enough away and sealed away that we won't have to worry about electrocuting anyone that's using
how
it.
much power, I mean, what kind of power current are you anticipating?
Nothing more than 12 volts, hopefully.
Well,
That's not something we've looked into yet, just because we haven't finalized our list of materials or really know the entirety of the system yet, just because we need to work with Mizumi a little bit more and make sure that we have the full scope of like what materials we should be using from them. We just have a preliminary list right now, and they might come back to us and say, like, we think you should use this air pump instead of this one, or this water pump and not this one, that sort of thing.
awesome. I just sort of think about power, like,
Yes.
the only thing that can be running in this office is this, like, no making coffee.
I don't think that would go very well in an office setting.
Suck up all the air as possible.
We are awesome on time, but we have any more questions or comments?
So I get to ask them questions all the time.
Yeah. Okay, very good. You want to say goodbye to John?
Oh, bye, John.
I am going to
Oh, I need the part. The last one.
stop the recording. Okay.
Thank you so much.